The podium mic is not live. Can you please turn it on? All right, we're going to get started, so if you could please find a seat. All right. Hello, I'm Aeowyn Kendall with Aztech Geothermal. Today, I have the honor of moderating this panel of international experts. And we will be discussing a fascinating and perhaps underrepresented topic. How does the ground heat exchanger actually function once it's been installed? This is something that perhaps as an engineer, and the engineers in the audience may feel similarly, we don't always think about as much as we should with system measurement and verification. So today we'll be hearing from Dr. José Acuña, who will be giving us a Swedish perspective on 3D coordinate measurement and verification, as well as temperature measurement from a perspective of putting a device down the borehole. And then John Williams from the USGS will be giving us the American version of that. They have their own device that they put down the boreholes to do borehole mapping. We will next hear from Isabel Varela of HEET, who will tell us about the Framingham learnings that they have from their study where they do fiber-optic measurements on the temperature and other things that are very interesting. And finally, Connor will wrap us up with a perspective on real-time system monitoring if you just use a temperature sensor and flow meters on an installed system, so there's nothing actually installed in the borehole. And I will pass it off to José.
Thank you, Aeowyn, and thank you, NY-GEO, for the invitation. Thank you for a great conference. I am José Acuña. I am an advisor and researcher within ground source heat pumps at the Royal Institute of Technology in Stockholm. And I will talk about these two measurement techniques. The first one is the deviation, and I will give you a bit of a context to why this measurement is relevant in Sweden. The picture on the left is a residential single-family house area where each red little line that you see is the projection of the boreholes seen from above. So plenty of inclined boreholes drilled at pretty much every single villa. It's a saturated market today in Sweden. Pretty much all single-family houses have at least one sort of boreholes, but many times ground source boreholes, ground source heat pumps. As you see the inclination there, you might wonder why, and that's because you come in conflict with your neighbors. So you search for depth, you search for ground volume, and you try not to have any influence from your neighbor installations, as most of them are for heat extraction. That would be like our saturated market is actually decreasing market size. There is no more place for ground source heat pumps in villas. However, we have an increasing market in the large residential and commercial. That's more or less illustrated with the picture on the left and the right-hand side. That will be downtown Stockholm. You still see these red dots or red lines where the clusters of boreholes have been installed for most of the times either even heat and cold production. So again, it's limited areas for drilling, neighbors that also want to drill, and then the inclination becomes a relevant aspect to include in your design. And then the question comes to how deep these boreholes are. You see the projection, and we have statistically seen a very clear tendency of increased borehole depth with time. So in the last 40 years, boreholes that were before like 100, 200 meters deep now are 300, 400, even 450 meter deep as a standard depth for all these type of installations. And the measurements normally once they are done for geometrical, let's say, documentation, you have the design positions, which in this case is the red dotted lines for 3 building blocks that share a common ground source heat pump site, and then the black line that displays actual borehole directions. And John will tell you a little bit more about this. We measure it with a magnetometer, which is an instrument that you just send down with a winch, and it orientates against the magnetic north, and gives you the X, Y, Z coordinate at any point you want. It's quite easy instrument to use. And normally done for documentation purposes. It's not something that is done for regulating or controlling things. It's more documentation that people have understood the need of. Also because there are a lot of on-the-ground infrastructure like tunnel, subway, and others that you need to coordinate drillings against. The other measurement technique that I was planning to tell you about is distributed temperature measurements. In our case, most often with optical fiber cables. And it's a cable that you send down either in a naked borehole or inside the U-loop, and then you log temperature for different purposes. The first type of measurement you get is the undisturbed ground temperature profile. So you have, for example, in this case, three measurements in Stockholm. A and C are 2 boreholes where you have a densely populated area where there have been buildings for many, many years, and these buildings have been leaking heat downwards. So that's the reason why you see a warmer borehole on the top until certain depth. The depth of that inflection point actually depends on how old the buildings are, because this front keeps traveling downwards about 1.5 meters per year. In the middle, on the other hand, you have a borehole in outside the city where you see the geothermal gradient pretty much from the beginning. And this type of installation, the measurement is normally done in connection with a thermal conductivity test. So besides connecting the rig, you put the cable in one of the 2 pipes, normally the downward fluid, which is a bit warmer, with a T-junction. And then you measure the undisturbed profile and then the rest of the measurement. And once that is done, what you see is this type of picture. Down here, you see the period of heating during the TC test. It's about 48 hours. And during that period, you have an upper chart here with depth and time. And then you can see in color a temperature scale. So the undisturbed borehole will be on the very left of the graph, cold. And then you start heating the ground, and you see how fast or how slow the ground heats up at the at different sections. In this case, every meter. And you can then define or identify sections, for example, with very high thermal conductivity. For example, at about 50 meters, the borehole pretty much does not heat up at all. You can compare it, for example, with a section at about 150, where the borehole becomes very much warmer, indication of low thermal conductivity, for example. Then during the recovery phase, when you shut down the heat injection, you can even see which parts of the borehole actually cool down faster and identify fractures or groundwater flow. For R&D, this is also a quite common measurement technique. Normally, the fiber then is installed in all parts of the borehole heat exchanger, downwards, upwards, and outside the pipes. This is an example for a heat extraction profile where you have a fiber that shows you the measurement in a specific time spot, and you see how the ground responds at different depths. So you have a very cold fluid during heat extraction that gets warmer all the way down, continues warming up on the way up. And then you have the measurements with a cable that is located outside the U-pipe. And this type of profile helps the researchers to optimize the flow rate, optimize the pipe dimension, and the depth of the borehole. The compromise between these 3 is very clearly visualized with this type of measurements. Another type of measurement is permanent commercial measurements, where you can actually monitor boreholes pretty much forever. Once these fibers are there, normally they don't come up when you do permanent installations then. And in this case, it's a thermal energy network in a university campus where several boreholes have been instrumented with this technique. And in this way, in this case, since it's permanent, normally the pipe and the fiber are sent down parallel and you see the cable in this case goes both down and up for measurement uncertainty reasons. And this measurement in this case would look more or less like this. Here you have a heat flux versus time chart. So here you can see when we are extracting or injecting energy. You have a timestamp identified with this pink bar that is moving to the right from early September to February. And then with the colors down here, you have the depth of the boreholes and the temperature scale. And you can see at each time step what is happening in each of the boreholes. In this case, we were starting in early September. It was the end of the cooling season. The boreholes were relatively warm, and now as we move from the cooling season to the winter season, you see that the borehole starts heating up, cooling down. And this is quite typical. It's quite overkill to do this in a commercial site, but you could still have the fibers and come a couple of times per year, perhaps at the end of the winter season and at the end of the summer season, and compare how these profiles look like and then draw some conclusions. It's normally giving valuable information. But in this case, was a research site that was then kept the measurements for demonstration purposes. So that was my last slide. I would like you to take with you the fact that there are many, many things to learn about our fantastic energy source, the ground, and we need to measure more so that we can argue back how good this technology is. Thank you.
Yeah, I want to thank NY-GEO for inviting me today, and thanks for putting this on. I think it's really an honor to be one of these panelists for this great group of people. What I want to do is give you a real brief overview of the hydrogeophysical tools and data that we're using for geothermal mapping for a cooperative project we have with NYSERDA. In cooperation with NYSERDA, we are compiling, collecting, and analyzing geologic maps, borehole logs, well yield tests, and thermal conductivity tests, and other associated data to inform geothermal development in New York. We've selected 3 multi-county areas representative of the Ontario lowlands, Allegheny Plateau, and the Manhattan Prong Hudson Highlands. Our sources of information of geologic maps, borehole, and well data include the New York State Museum, New York State DEC, and USGS databases, and published and unpublished reports. We have an interactive web-based mapper in development that will present the wide range of hydrogeologic information that we're collecting. Of course, depth to bedrock mapping is an important component of the investigation, and we have a leg up in the southeast New York study area in that we've published digital depth to bedrock and overburden maps for the 5 boroughs. which include Manhattan and the Bronx, which are our focus county areas in that area. These maps were developed from thousands of logs from borings. As you can imagine, in New York City, there's a lot of construction. So we've taken that information. And then we also complement that and supplement that information with HVSR passive seismic measurements, which are a quick and easy way to get an estimate of the depth of bedrock and overburden thickness. Essentially, the seismometer used is essentially a very small seismometer that you put on the ground, and you collect 20 minutes of data, and it measures ambient noise. So it's a three-component, and there's a fundamental frequency that the Earth, in response to that ambient noise, oscillates, and that fundamental resonance frequency is directly related to the thickness of the overburden. We're going to take the same techniques up into Westchester County and the two other focus areas. In Westchester County, it's mostly water well information from the New York State database and from NWIS, and again, and that's the same for the other two, the Allegheny Plateau study area and the Ontario lowlands. And again, we'll complement that with passive seismic measurements. So we've digitized available bedrock maps in our three study areas. Obviously, the Manhattan Prong area is the most geologically complex from a bedrock perspective, with faulted and folded metamorphic rocks, including schist, marble, and gneiss. Fortunately, that's one area that we have good bedrock geologic map coverage at 1 to 24,000 scale. We go up to Westchester County, and we probably have 50% of the county covered by bedrock maps. And then in the other areas, the Allegheny Plateau, there's very few detailed maps. And then up in Ontario Plateau, there's some more. As part of the project, we are collecting and analyzing a suite of hydrogeologic logs from geothermal bores as the opportunities arise. Here's the first one that we measured. It was at the Westchester Bronx border. It was an 880 feet deep bore, closed loop test bore in schist. We use optical and acoustic televiewers along with other standard logs such as caliper, gamma, and electrics to delineate bedrock lithology, the fabric, and the fractures. We then also do flow meter testing of these boreholes under both ambient and pump conditions. And the flow meter that we use has also built in to it fluid connectivity and temperature measurements, so we can get all those at one time. The acoustic and optical televiewers also, they have a deviation package built in, so you're getting that information as well. We can see on this borehole, it was pretty near vertical for the first 400 feet, and then it started to wander off. It ended up 50 feet off center at its total depth. From 2000 to 2010, we collected the same suite of geophysical logs from over 50 boreholes in Manhattan, Bronx, and Westchester County. Most of these were 500 to 600 foot core holes drilled for design of the New York City water tunnels. The log analysis demonstrated a strong relationship between bedrock foliation in these metamorphic rocks and hole deviation. Here we see two examples of those, 34th Street and 37th Street, and you can see the foliation we plot on a Schmidt lower hemisphere. The foliation is dipping to the west, and the borehole deviation is going to the east. And what's very interesting, 3 streets apart, the one hole is deviating 20 feet off of center, and the other one is 80 feet off of center. The bedrock geology in the Allegheny Plateau and Ontario lowlands is simpler. It's essentially sedimentary sequences that dip gently to the south, mostly shales and sandstones, but up in the interior lowlands, you also have dolomites, limestones, and evaporites. Here we have the advantage of gas logs, because it's a gas-producing area. So we have great data from there, and those typically have gamma logs and then drillers and geologist logs. And we also have a bunch of core holes around the Rochester area for their sewer system with very detailed information. And then, of course, thousands of water wells, both from the USGS database and the New York State. So we've combined these together in this simpler geology compared to Manhattan, into a 3D bedrock model of the subsurface. And here's an example of a cross-section generated from that. And we're going to have a mapper that you could just essentially put a point on a map, and it'll give you a virtual borehole, or if you put 2 points, it'll put it across cross-section. So our next thing is that we need to do is hang all the information of the different water types, freshwater, brine water, black water, and gas zones that we see in these areas, and hang this onto the 3D model. We've logged 2 boreholes, 2 geothermal bores in the interior, 3 in the interior lowlands, and 2 of those hit large quantity of salty water at relatively shallow depth. This well is at SUNY Oswego and hit a couple hundred gallons per minute of very salty water, and you can see it's from the acoustic telegraph, it's a bedding plane. Here's the second one that hit salty water. This was at Lyons in Wayne County. We also measured electrical conductivity profile as well. So at this site, there needs to be, at this site and other similar sites, there needs to be an economical, environmental, sound way to handle this. Moravik Geothermal, after multiple meetings with multiple divisions in the state, DEC and US EPA, got permission to re-inject these waters back into, and that project just started, so stay tuned for the results. So that's all I have.
Hi, my name is Isabel Varela. I'm with HEET. HEET is a nonprofit with a mission to evolve our thermal energy system, and I'm excited to share with you data from the boreholes in an operating thermal energy network in Framingham, Massachusetts. So the work that we present today is part of Leg Up, or Learning from the Ground Up. It's a research consortium that HEET leads and is focused on the study of thermal energy networks. We collaborate with a number of different research institutions listed here, and we're collecting data from thermal energy networks that are utility-led in Massachusetts. We're creating tools to simulate these systems, and the different research institutions are focused on different aspects of the impacts of TENS, including on the electric grid that has been discussed a lot in this conference, but also on cost, on health, on equity, on ecology. So now let's go to the data. The Framingham project is the first utility-led retrofit system that is operational in Framingham, Massachusetts. It is operated and owned by Eversource, with whom we collaborate with. So roughly the characteristics, it's a single pipe with water connecting buildings. 36 buildings are connected. The perimeter is about 1 mile. We have single-family homes that are connected. We have also apartment buildings from the Framingham Housing Authority and commercial buildings. There are 3 bore fields with 90 boreholes in total. And what we did was we collaborated with Eversource and with UC Berkeley, the SOGA Research Lab, to install fiber optic cable that José Acuña very nicely described the technology. So this is kind of a case study. So we have temperature measurements down the borehole, and the plan is to look at this data throughout the lifetime of the field. So briefly, what is the lifetime that we have now? So the commissioning timeline. We started recording data in July of 2024, and the commissioning of this 10 project is multiple months. So it's connecting all those buildings and connecting the different bore fields. So the data will show that part as well. So the commissioning goes from July until April of 2025. This is the first bore field, the Normandy bore field. It's located in the top left of the loop. It has 2 platforms, and the bores are deviated with a pyramid configuration. So what we see is at the beginning, there's a period of testing. Some of the boreholes are being bypassed. The temperature of the subsurface, when it's undisturbed, it's 12.5 Celsius, it's your 55 degrees Fahrenheit. And then we have the main events of the commissioning. So you can see that throughout the spring, we still have commissioning happening, and we only really have the full system in the summer, from the summer of last year. So we don't yet have a full year of the system fully commissioned. We do notice that there seems to be more, the ground is heating more than it's cooling. So things that could be causing this, 1, well, the commissioning process. 2, many of these buildings did not have cooling before, so they may be using their cooling more. And 3rd, the heat pumps were installed with a backup electric resistance heater, and depending on customer usage, that system may be going on and off, taking away some of the load in the winter, if you will. And that's kind of just the trend. We can also look at this data in depth, like the profiles that José showed. And what we notice is that in the top 50 meters, there is more thermal interference. Now, this is expected, and it's nice that we observe it, because these boreholes are in this pyramid configuration. They're closer together at the surface. So we notice this in the summer when the ground is heating, and we also notice this in the winter when the ground is cooling. And we can move now to the second bore field. So it's beautiful data. We have a period of time when the bore field, we're just recording data, the bore field is not online yet. And then the bore field becomes online, and we have the blue is the operational well, and the red is a control borehole. It's non-operational. And we see that the control borehole has less temperature change compared to the operational one, as expected. We also see that there's a time delay of about 2.5 months from the peak of the control to the peak of the operational well. We also observe that the temperature change in the ground for the operational well is less than what we saw in the first bore field. Now, the biggest loads for this 10 system are actually happening between the 3rd bore field and the 1st bore field. That's why the first one has more of that temperature change in the ground. And we can move on to the 3rd bore field. Now, all of the buildings have been connected by the time this bore field goes online. All the other bore fields have also been connected. We have some data gaps just from the issues with the interrogator, and we also notice that there's a smaller temperature change compared to the 1st and the 2nd bore field. And there's more detailed about this data and this work with lead authors from UC Berkeley, our collaborators, and it's in the Stanford Geothermal workshop from February this year. So we invite you to read that. So briefly, I'll mention the first bore field had these pyramid configuration. The 2nd and 3rd are actually vertical. Just very briefly, HEET is collecting high-level data from these 10 systems to share knowledge, including high-level temperature data. And that's in this geodata bank database. So briefly, the system is operating well. The 10 system actually has an electric boiler backup that has not been used from the time that operations started. The DFOS temperature of the subsurface, it helps us understand what's happening, and more importantly, how can we optimize the operations of the system going forward. We are looking forward to having a full year of fully operational, fully commissioned, and other things that we want to do is, can we quantify thermal storage and mitigation strategies, understand better and mitigation strategies for the thermal imbalance that we observe in that first bore field. And for example, working with controls of the system and pump rates would be a way to go. Thank you.
Okay. Well, first off, I'd like to say I'm grateful to be on the panel with such bright and interesting people, so thank you, NY-GEO. So my goal here is to bundle everything up that my colleagues have said and slant it and tilt it towards ground source heat pump system design. So typical design methodology is you start with, you probably heard this term several times over this conference, is an 8760 hourly energy model. You try and quantify your heat loss and heat gain of any particular building, whether that's for a residential, commercial, or district system. Try and really understand the heat loss and heat gain. Then you go to site, you do your thermal conductivity test, try and understand your thermal properties of your particular site. Use your favorite ground heat exchanger sizing software, whether that's GLD or Transys, or pick your favorite. But underlying all of these softwares are two main algorithms or equations. One is called design day, and the second is called G function, and they're theoretical. So in nature, they have some limitations. You do your AutoCAD drawings, and away you go. Right? You go on to the next project, or you help with commissioning and actually constructing it. But underlying all of these designs are this static 8760 energy model. And so that can be challenging to use that for a dynamic system, but it is the best we can do. And then also ground heat exchanger sizing softwares do rely on these theoretical equations that I mentioned. And as an industry, we tend to prioritize simplicity, which makes sense inherently. But what I'm going to talk through a little bit is data-informed designs. And what John talked about is borehole verticality. And so we can use that borehole verticality information to inform borehole spacing on our particular project. John mentioned deviations such as 80 feet. Obviously, you're not going to space your boreholes at 80 feet, but if you have that information, it can help inform some design decisions. José and Isabel talked through DTS, distributed temperature sensing, and you can use that information to inform the ideal borehole depth of your particular project. If you have that information during the thermal conductivity test, you can use that to help inform your design. Next, you can actually monitor the energy flow into and out of a ground heat exchanger and replace that with your 8760 energy model. And then you're changing from a theoretical building energy model to the actual ground heat exchanger loads that it's seeing. And so these theoretical models, they help with the initial design, but the empirical models, the actual data, help with validating real-world performance. And here's an example of that, where we have a condo in Toronto. We have 40 bores at 600 feet below grade, water-to-air heat pumps in the suites, and natural gas boiler for domestic hot water heating. I have a flow meter for flow rate and 2 temperature sensors for our temperature differential. Delta T and flow, we can get our energy, or that's how you get BTUs. This illustrates the differences in 8760 energy models with actual performance, and it changes, right? It's a dynamic thing, so month by month, these loads change, and we have been seeing quite a bit of deviation between the 8760 hourly energy model that's used for design with the actual loads that are put upon these ground heat exchanger systems. I think Isabel mentioned they're seeing that in Eversource right now, and maybe that's because some auxiliary usage that wasn't intended in the original design, but we are seeing quite a bit difference from the theoretical model that was used in the design phase to the actual performance of these systems. We talked through those two equations, G function and design day, and when you apply the actual loads that the ground heat exchanger is seeing versus the 8760 loads through that algorithm, you run that algorithm to calculate the future ground heat exchanger temperature, you do get differences. But again, that's because the energy loads are quite a bit different. Then if we have the actual temperatures that are coming from the ground heat exchanger, we can compare the actual temperatures with those theoretical projections. And so that's what you can see here. And again, it is a little bit different, but at the end of the day, I guess what I'm trying to articulate is that it's good to monitor these systems and using all the data you can get to inform future designs so that you can improve and we can improve as an industry. So that's all I got. Thank you.
All right, we will take questions at this time.
Mark Williams, CT Mel Associates. This question is for Mr. Williams. First of all, a note of thanks for your decades of research in borehole geophysics. It's really improved the science and general people understanding the data that you collect. My question for you is that it's been presented, I think it was the first talk we attended yesterday, that geothermal projects are not one size fits all, and partly because of the geologic environs. And I'd like to know, with all the great data you've collected, is there plans by funding from NYSERDA or the federal government to fill in the gaps on the different physiographic provinces you've already got a snapshot of?
There it goes. Yeah, so when we first discussions with NYSERDA was, well, let's do the whole state. And we said, well, let's take a phased approach. So we're very much in favor of continuing that phase. Obviously, the Hudson Valley is a prime candidate, filling in, like the lowlands up in the north of Adirondacks. Yeah, so from a federal point of view, the major effort has shifted a little. Well, it has gone to more of the high temperature, the really hot stuff. The closed loop stuff, we keep on having discussions with groups that are doing geothermal, but their major emphasis is the open loop geothermal, the hot stuff. So we'll keep banging away and hopefully, look at the population that's going to be dependent on closed loop. We definitely need more attention there.
So I'm Josh Woda from the USGS. I've got a question for everyone except John. Sorry, John. So I'm really fascinated by all the temperature work that you guys are doing downhole, the DTS especially. I guess especially Jose, where you guys have maybe been doing this research for a while, what do you think you guys are learning from these efforts, and how do you envision it will help optimize performance in the future for these systems?
Thank you. Well, yeah, that's certainly the case. These type of measurements have been done pretty much since about 2007. There are lots of experiences where the data is collected sometimes without knowing why, but sometimes because the clients have realized that there might be information that can help. At the very first stage is a design tool, you could say, so it helps pretty much do a better design, understand the conditions so that you do the design. That will be the straightforward, coordinating the measurement with the views from or the notes from the driller. But once the systems are in operation, what we have seen is that the profiles that you calculate with these functions that Connor was telling you about, normally they deviate. They come from a black box approach pretty much, which deviates significantly from what you see in these type of measurements. That doesn't necessarily mean that the sites operate differently than calculated, but it helps a lot to see whether these assumptions that are made are true or not. The difference, I would say, straightforward in the operation will be comparing profiles during winter and summer. Winter drilling, heating or cooling cases. Normally, they differ significantly, and then that helps you perhaps to operate the field in a little different way depending on how the hydraulics are connected. I think for giving you a more detailed answer, it should be more project specific because it's quite different from project to project, but it adds value with a very low cost, I would say. Yeah.
So for the Framingham project in particular, we saw that the main bore field has a thermal imbalance, right? So one thing that we can do, one thing that could be done is, for example, some of the other bore fields, the thermal change is much smaller. So the pump rate for those bore fields could be, for example, increased compared to, right now all the bore fields are at the same pump rate. So you could play with the controls to make it so that the bore fields that are right now having a smaller temperature change could have higher pump rate, maybe used more, and you could lower the pump rate in the main bore field, for example. But we are learning from these observations, there are many things that could be done. The other one is the backup electric resistance heaters that right now have two modes, a ramp-up mode and an emergency mode. So ideally, they would only be used in the emergency mode and not in the ramp-up mode. So making those changes, for example, in the Framingham Housing Authority or in the commercial buildings, so things that can optimize potentially the system. So the data has been very useful. We don't have the full year yet, but we already have ideas as to what could be done. And of course, it's operated by Eversource, but we'll collaborate with this data.
I would also like to add the fact that, as you could see in the measurements, you actually can see groundwater flow as well. And there are areas where this is a sensitive question, which is requiring controls from the municipality, for example, that you have to deliver measurements to show that things work as the designers thought about. And these type of measurements are very strong arguments to show actually that things work or does not work, of course.
And I would say validation of where you think you have groundwater flow or the heat conduction is indicating, correlate that with the borehole geophysics that you're able to actually map and look at those fractures and estimate their transmissivity.
So Rick Clemenzi, Geothermal Design Center, and I think this is for John and possibly Jose. So one of the things that we're doing is trying to quantify the heat capacity of the ground, and we're doing that with digital twin modeling. And but one of the things we're trying to do is to prove it. And of course, we could probably prove it by going and collecting core samples down the bores. But I'm wondering if you gentlemen know of other tests that we could be able to do using some of the oil and gas industry testing, gamma radiation and stuff like that, that could in any way determine what is the actual heat capacity. So this is getting to where we're actually sort of starting to design these systems more for storage and whatnot.
Yeah, I would say, I think I saw one thesis that tried to do that, to take the oil field geophysical logs and regress them against the thermal conductivities. So I think there's some hope there. Gamma obviously is a very easy tool to run, and it essentially gives you clay content in many environments. And it would seem logical that thermal conductivity is related to clay content. So I think there's some hope. We need more data.
For Gino DeRezzi from Ground Heat Thermal City. Back 30, 40 years ago, we used to drill with the augers, and we used to drill 10, 15 feet apart. Occasionally, the cuttings or the boreholes that we drilled the day before would come back up, and so we didn't know there was deviation in drilling. With the regulations that they say should be 10 feet apart from the property line, knowing that basically in a 800-foot hole we could be off by 80 feet, there could be a need for a technology, hopefully inexpensive technology, to offer to the drillers to be able to be as accurate as possible in their drilling. Right now it's a secret, but it happens. And hopefully, occasionally you might lose a hole or two, but you re-drill it, but it could be in somebody else's property or underneath the road somewhere. So, are the technologies out there that could help the drillers?
Thank you. Well, yeah, these are commercial tools. The ones I showed rather, I would say, every day used in the mining industry. I would say they are completely available. I think the ones you showed, John, perhaps are a little bit more scientific. But from my...
Same measurement, though. Yeah.
Same measurement technique, exactly. I would say the drillers can drill as designed if they want. That's what I have seen in these type of measurements. If no one requires anything, you find large deviations. If this is monitored in some way, the drillings are very much in line with the design. Of course, there are some factors that they cannot control, but we see very, very good measurements, or let's say in line with design when there are eyes looking, independently of the depth, which is an important factor you mentioned, John, that actually they start deviating more and more the deeper they are, which is the case for the Swedish boreholes, but still they do very good job on respecting the design when they have eyes on them.
I'd be curious on Kevin's response to that, and then I guess one thing I'd say, and maybe this is a crude answer, is ignorance might be bliss in some cases, right? If you're going into other people's property lines, you may not want to know that. But Kevin, I'd be curious on your take.
I think a lot of people share that opinion.
Knew it was going to happen. Kevin Moravec, Barney Moravec Incorporated, New York GEO board member. I think that you're right, Jose. If there's eyes on it, it gets done in a certain way. The biggest thing that we see, and John just looked at one of our boreholes at Lyons, new bits matter. Speed of drilling matters. And so when you're in a race to get productivity done and you're trying to stretch out the length of your drilling technology, it doesn't really matter what it is, that's typically where you start to see more and more of that deviation. You see more spirals, you see more kicks. Having information on different sites of where some of those planes are and what can cause that kick, at the end of the day, unless you have a way to steer the head, it's going to do whatever it wants to do. Heavier drill steel also helps you stay straighter.
Yeah, so the well we just logged, that Lyons one, we also did a 400-footer that they just drilled, and I don't know, Kevin, if you even saw it, but it was like 1 degree off. So that's in part the geologic environment, but it's also reflects the driller as well. So.
That actually happens the bottom 30 feet. Sorry, yeah, that last little bit was a formation change. We went from shales into a really hard limestone, and that kind of kicked it just a little bit.
Apologies, I'm going to jump in. We still have time for your question. Jose, I'm curious, in your experience, now that we've heard from Kevin, what is it that the drillers do differently when there are eyes on them?
Well, I don't think I am the proper person to answer that question, but I know that as Kevin mentioned, the pressure that they use to drill, they can decide it, actually. That's a big factor, as I understood. That defines the speed at which you drill. And then I guess it's a matter of experience, that they hear things that other people cannot hear. And then I know there are mechanical tools to also add to the drilling rigs that also help. I don't think I'm the right person to describe them, but I think there are plenty of people here that can tell you about it, and they also help to give better direction.
Sure, thank you.
Thanks, guys. This is Dan O'Rourke, CDM Smith. I guess it's more of a question for John. With your work with NY-GEO, is there any, I guess, effort looking forward to create some sort of database for borehole depth, geology, thermal conductivity as it relates to geothermal, right? Because around this area, for sure, I mean, I'm spoiled rotten with the amount of data we have with the USGS, you know, having all the data that you guys have done. One thing that I think would be a nice addition to that is like thermal conductance. Now that GEO is becoming more and more prevalent around these areas, you know, if that would be, I think, super useful to help folks early phases of design before they go out and drill a test hole and that kind of thing.
That's the major objective, is to develop this database. And the thermal conductivity has been kind of a thorn because it's just not reported. Everybody has their own database, and there's no way. You know, we've got depths of wells and so on. And what happened in New York, at least, anything above 500 feet, you didn't have to report it if it was a geothermal bore. Greater than that, you did. So there's a whole lot of data out there, including thermal conductivity, and we're going around and talking to people and trying to get that data.
Yeah, Could like NY-GEO make that a requirement for funding, right? Like if you're, you know, as part of your, sorry for whoever I might be pissing off, but yeah. You know, in terms of like, you know, you got, you know, as part of the NY-GEO project that they're giving funding for, or Con Edison's giving incentives for, you know, one of the things you have to do is report your thermal conductivity.
I'm not a regulator, but that makes a lot of sense to me.
I'll just briefly mention that in Massachusetts we have something similar. So the DEP is collecting the data from the boreholes that are drilled, but the reporting of the thermal conductivity is not consistent. So it would be great to have that. Yeah.
Yeah, we've talked to New York GEO and see if to get those members, and they've created a database to put that information in, and we're actively talking with NY-GEO as well. Yep.
And I'll chime in on that too. So it's been a struggle, obviously, trying to get that data given to the DEC. Like, we are working actively with both the deeper than 500 foot and what will eventually be the shallower than 500 feet of having some mandatory data being reported to these agencies for public consumption.
Yeah, I mean, I would just add, you know, at least in some areas of North Carolina, like where we are, even where we are, the geology changes, right, within a kind of a close area. So it really depends on your very high resolution geology location, exactly what you're going to get. So it's like, it's one thing to collect it, and you have some general understanding of that, but you're not going to know what's going to happen at a certain site. You know, at least where we are, we only have 2 geologies. Over in Raleigh, they have 3 different geologies, and it can change like by the block. So it's a kind of hit and miss depending on where you are.
Lively room.
John, there's also I don't know if you
are?
looked in, Mark Williams, CT Mel Associates. There's also We're not related. The New York State Geological Survey through the New York State Education Department also has a database, and they do have some limited application of thermal conductivity data. They have a database that doesn't seem to connect to the DEC or NYSERDA. It's a point of contention amongst the geologic community. But they have a database called ESOGIS. I think they're renaming it, rebranding it to some point. But it has a lot of the oil and gas logs. It has some of the salt drilling logs of the Finger Lakes area. And that also could be the beginnings of a substantial database.
Yeah, I mean, I think the trick is that we need a home for the database, right? I mean, like, in my opinion, I'm a geologist, so I love the USGS, and you guys have the greatest platforms that are out there on the web that anybody can access. So it would be like, not to pin it on the GS, but it'd be up to you guys to or NYSERDA or, whoever to provide a home for that database for people to access.
I do have a question. Kevin Moravik again. So Jose, from what I've heard, most of those boreholes, they're open water, right? You don't use any grout, any thermally enhanced product in there. Is there a way to maybe project how those boreholes would perform differently if you used, I'll say, our version of it with thermally enhanced grout?
Yeah, that's true. We do grout, but it's seldom. It's the rules or the standards in Sweden say that we grout only when needed. So most of the cases, at least, have been identified historically that is not needed. Of course, there is a way to calculate the differences with or without grout. We know groundwater fill boreholes well, and we know how groundwater moves with temperature, has density difference-driven water movements and so on. And when you grout and you have like a solid filling material outside the collector pipes, the things become much more simpler in my opinion, because it's thermal conduction. So yeah, definitely there is a way to see clear differences and quantify whether grouting would be of benefit or not. But groundwater flow helps to equal any commercial grout that I can see in the market today.
Last one.
Paul Chipoco, New York Power Authority. This question is for Connor. In the slides, you were showing a project where the initial heating and an actual heating, there was a big difference on, it was cooling dominant system, I'm assuming, because you could see that in the chart. Can you talk to why there were such a big differences in the actual, on the initial?
Yeah, great question. The main difference is auxiliary backup usage, unexpected auxiliary backup usage. And I think Isabel touched on that a little bit in the Eversource project. It happens a lot, especially on these hybrid systems. Designers have good intentions with hybrid systems, but when a building operator gets their hands on their system, there's no, unless there's governors in place to limit backup usage, it tends to be run more than expected. So that's what we see a lot in the wild, is these hybrid systems tend to be not the percentages that the designer had intended when they designed the system. So good question though.
All right, thank you very much. Let's give them a round.